Good morning, everyone. This lecture is for CS 451 and 651 students only. If you are in 431 or 631, your lecture will be at 11:15. All right, the plan for today is to learn a little bit about Spark, and I will show you a little demo of how we program in Spark and we start learning basic things about Spark. All right. Let's revisit RDD, which is a key concept in Spark. If you remember, RDD is basically the data structure that keeps our data in a Spark. It is a distributed data structure, which means that the content of your data is actually stored on multiple physical machines on a cluster. It's not on a single machine. The reason is RDD is in the memory, right? And because we work with the big data sets, we may not be able to load that data into the memory of a single machine. And as a result, we use multiple machines. So an RDD, this is the logical view of an RDD. This is how you should think about an RDD when you program, okay? This is the logical view. So an RDD like this is divided into chunks, okay? These are the chunks that are stored on different machines. Each chunk is called a partition. That's the correct terminology for it, okay? So your data is divided into partitions. If you created this RDD by reading a file from HDFS, for example, each partition will contain some lines of data, right? So for example, thousands or millions of lines, and then the next partition will have millions of lines if it's text, right? If your RDD contains key value pairs, it will be key value pairs. If it's integers, it will be integers, right? It depends on the data type. But the idea is that data is divided into chunks. And the default partition size in a Spark is 128 megabytes. So each of them is typically 180 megabytes. You will see later on, especially in the next lecture, when I talk more about creating an RDD from a file, you will see that each partition is basically an HDFS chunk, right? So because HDFS divides your file into smaller chunks, right? And that machine, when it reads it, every chunk of data in HDFS will become a partition. So basically, the partition size will be the size of the chunk in HDFS, which is typically 64 megabytes or 128 megabytes. On data size, 128. All right, so this is the logical view, right? So, okay, so my data is divided, it's partitioned into partitions, okay? But what is the physical interpretation of this? So if you remember, we said we have a driver program and many worker machines, right? So for an RDD like this, one example of how these partitions can be distributed on different machines is something like this, right? So each of these worker machines can take care of one of the partitions, right? In this simple example, I gave 2 partitions to each machine, but in practice, it may not be balanced like this. It might be 0, 3, or no partition for some of the machines if we don't use all of the machines for that particular task, right? Any question about this? Let's make sure we have a good understanding of what RDD is, both in the logical view and physical view. Questions? Are you good? Are you happy about the definition of RDD and how it works? And then when you load an RDD like this and you apply different transformations, basically each worker node will apply that transformation on all of the partitions that it is responsible for, right? For example, this guy here will process 2 and 5, right? So, and as you can see, it's a completely parallel operation. Obviously, there are some operations that cannot be independent, like reduce by key. There we have shuffle, like Hadoop, obviously, and we create new RDDs, and we'll talk about those. Those will be more complicated. All right. So last time we talked about caching an RDD, right? Saying that if you want to reference an RDD multiple times, it is recommended that you cache it because Spark may get rid of that RDD. And then the second time you access it, it has to recalculate it again, potentially all the way from HDFS again, which will be very slow. So if you can cache, obviously you gain performance, but it's really a trade-off, right? How much memory do you have, right? So you have to spend more memory on caching, and this graph here shows you the execution time on the y-axis. So lower is better, and then the x-axis is basically how much we can cache, right? From no caching all the way to fully caching everything, if we can, obviously, right? And you can see it's a huge performance gain from about 70 seconds down to 12 seconds, a huge improvement, right? So how should you use caching in your program? Well, very easy. If you reference something, an RDD, more than once, cache it, or at least see if it makes sense. It's a good candidate. The other issue we have in Spark is that we do not store stuffs on disk all the time, like Hadoop, right? And we try to keep stuff in memory as much as possible. So it is very likely that one of the worker nodes die during the operation. And what happens is that some partitions will be lost, right? And as a result, we cannot proceed anymore, right? Some of the data is missing. The way Spark handles this problem is not by replication, but rather by recovering from the error, by reproducing the error. So Hadoop and HDFS, they have replication. So they keep copies of the data, right? So if something is lost, they have another copy. Spark does not do that. Instead, it memorizes, okay, this lineage information. And what that means is that it remembers how an RDD is created. For example, this RDD messages, it knows that it's coming from this RDD, and then we apply filter on it, and we apply map on the result of it, right? So we read, for example, text file from HDFS, we apply filter, and we apply map. So it remembers this chain of operations. Now, if one of the machines die, right? And for example, we lose partition 2 and 5 on that machine. What it does is says, okay, I know how to recover that. Either it restarts the same machine and it comes back and it does it, or it assigns a new machine to it. It doesn't matter, right? The important thing is that when we have a working machine and we know which partitions we missed, we go ahead and basically try to recover it. How? I know that I'm missing this data, right? So I go back and see if this is available, because this one was created by an operation on the other RDD, right? Is this available or no? If this is not available, it's fine. The worst case is that we go all the way back to HDFS. We assume this is fine, right? Because we have copies and everything redundancy. So the worst case is that if something is lost, we go all the way back and recover those partitions from HDFS again. If there are some intermediate RDDs that can help us, better. It will be even a faster recovery, But if we don't have any intermediate RDDs available, no problem. We can still recover. Okay, so remember, Spark does not provide fault tolerance by replication, but rather by keeping track of how RDDs are created. Questions? I don't get any questions today. Did I confuse all of you? All right. How can we program with RDDs? I will show you some slides and we review them quickly, and then we will try to see how it actually works in Spark. Okay, I'll show you a quick demo. All right, so let's learn a little bit more about the Spark. One important concept that you need to learn is the Spark context. Spark context is basically the main entry point to Spark functionality. When you code, for example, you guys use Scala when you program in Spark, and everything you do is pure Scala, right? And how do you, and that's your driver program. How does the driver program ask worker nodes to do something in a Spark, right? It uses this variable, the Spark context, to get access basically to Spark functionality. I'll show you examples, okay? So when we are in shell, that variable is already set up for us, and I will use the shell today. So I can just use SC, and I can use it, as you will see, to create RDDs and do operations on the RDD. And if it's in a standalone program like your assignments, then you have to basically create SC. And it's typically provided to you in the skeleton code. So we have a question. Why did Spark choose this approach? I think you're talking about fault tolerance mechanism. I imagine this is less efficient than using replication method when recovering from a failure. That's a very good question, right? It's a system design challenge. So nothing is free, right? So it's always a trade-off between different things. As you pointed out, it is less efficient. We have to define that. What do you mean by less efficient? I think you mean it's slower, right? Because if I have a copy and I lose one replica, it's fine because I can quickly recover by reading the other replica, right? It's very fast. That's true. So in terms of delay of recovering, having replicas is typically better because here we have to go through the processing and calculate the missing partitions. But at what cost? The cost of potentially doubling or tripling the amount of memory that you need, right? If you want to keep a replica, it means that the amount of RAM you need is double, right? So that's a trade-off. So that's why they chose to recover in case something happens rather than using a lot of memory. Make sense? We got another question, Umaid.
Yeah, Professor, what if our original HDFS file failed or is lost? Like, since it tracks the lineage, so what if our original file has been changed, so it can't recover from that, can it?
So you mean what happens if this thing changed?
Yes.
So it cannot change, right? So so the files on HDFS are read-only. So, the only thing that can happen is that something might be appended to the file by the time we want to recover. Now, in most cases, it remains the same, right? It remains the same because it's read-only. You cannot just change some values in HDFS files. But if we add more lines and we have a failure, I believe that it knows the last state, like how many lines we had in that file, so that it recovers from the same state when the program started. But I'm not 100% sure. I have to double check this. Okay, but I believe that it recovers from the last step. So it knows that, so, and it's not a lot of information because all it needs to know was that how big the file was when we started, right?
Yeah, okay, sure. Thanks.
Makes sense? Yeah.
Yep.
Thank you. Good questions. Moving on. Okay, there's no more questions. All right. So for context, I'll show you examples of this. How can we create RDDs? Before we can use them, we have to create them, right? One way to create RDDs is to convert uh, an object in the host language. For example, if you're using Python, we can convert a list in Python to an RDD. Or if you're working with a Scala, it can be in a Scala list or in a Scala array, right? And you can convert that into an RDD. I'll show you more examples. The syntax for it is like this. So we have SC, the Spark context, right? So this is the reference. It's very important. That's how we can start basically Spark stuffs, right? And then this operation is very handy, parallelize, okay? It converts an object from host language to RDD. So the result of this thing, and this is Python, so it's a list in Python that contains 1, 2, 3. The result of this will be an RDD. So if I do this, for example, R, this R will be an RDD, right? That is hosted on the worker nodes, not my driver program anymore, right? And the content of that RDD will be 1, 2, 3. That's one way to create RDDs. So typically, this is just for testing, right? Because we cannot feed a lot of data to Spark this way, right? It doesn't make sense. So if this object already fits into RAM, why should I use a Spark? So this is used mostly for testing, right? Just to make sure that our program is working fine. The usual way of creating RDDs is from files, right? So we have a big data set that's hosted on the local file system or HDFS or some other services. So Spark implements many basically different APIs for reading stuff from different interfaces. So it's really cool. And the operation is text file and it has some other functions as well that you can look up. This is specifically for text files. So sc.text file and then local file or a collection of files, right? So all of the files in that directory or something from HDFS or even nicer, Amazon S3, something like that works as well. So if your data is on Amazon cloud, you don't need to download it, for example, first and then provide that address. You can directly provide the cloud address. Really cool, right? So that was the second and the common way of creating RDDs, right? And then, as I said, always we have something like something here, right? An RDD here. So we have a reference. I don't know why the resolution of this thing is so low. All right. So that's about it. So we create RDDs. And now that we have created RDDs, how can we perform basic operations? And please let me know if you have any questions. So in this example, I create an RDD using the parallelize operation because I have a toy example here. And I store that in nums. Nums will be the reference to my RDD. And still we're using Python for these. I'll show you the Scala version in a second. So now we have an RDD and that's the content and we can map, right, something. And when we say map, it means that every element in that RDD will be mapped with this function, right? And it says, take every element that you have and raise it to the power of 2, right? So compute the square of every element. So the result will be a new RDD, important. We never modify RDDs. RDDs are read-only, right? So that gives us a new RDD, and we call that the squares. And the values in that RDD will be 149 because we raise everything to the power of 2. And then another example is filter, right? Filter basically only keeps a subset of your values, right? Very useful in data mining because most of the time like 90% of the data is garbage. So we can use filter immediately to get rid of them. So here it says, take your squares RDD that we just created, right? And only keep these elements. So for every element like X, basically, if this statement is true, keep it, right? So it's if the mod of that number is 0, keep it, okay? The values of a squares RDD is 149, so only 4 matches this statement, right? So the even RDD, again a new RDD, right, will contain only 4. We have an interesting variation of map called flat map that's very useful. This is one application of it. I'll show you another application in my example. But what it does, and one of the differences between map and flat map is that in map, you apply a function on every element, right? So if my original RDD has 1,000 elements and you apply map, the resulting RDD will also have 1,000 elements. Makes sense, right? For example, here, if nums has 1,000 numbers in it, the squares will also have 1,000 numbers. Do you agree? Because it's a one-to-one operation, right? Makes sense? But flat map allows you to do other combinations. So you can go from one element to multiple elements. Okay, so it's no longer one-to-one. It can be one-to-many. Okay, for an example of that is this. It says, take the nums RDD. This is the original one that contains 1, 2, 3. Again, sorry for, I don't know why the resolution is so low. And then apply this. So it's again type of map. So it takes every element and it does something with that element, right? So what it does, it says, take X and for every element X, give me range of X. Okay, range is a built-in function in Python that range of X will give you a list of numbers from 0 to X minus 1. Okay, so if you give it 5, it will be 0, 1, 2, 3, 4. So it takes every element X and it basically replaces that with range of X, right? Or it maps it to range of X. For example, for the first number 1, it feeds it to range and it will be 0 only, right? Because it will be 0 to 1 minus 1. And then 2 will be 0 and 1. And then 3 will be 0, 1, 2, right? So you can see that I started from an RDD that only had 3 elements. I ended up with an RDD that has 6 elements, right? This was not possible in map, but possible in flat map. The resolution of the image is fine, but when I'm drawing or writing something, you can see the line is broken sometimes. That I don't know why. One question, Man, go ahead.
Yeah, hi, Professor. So just to make sure, the flat map is taking one element and mapping it to many, and then is it like flattening all of those like lists together to produce one result list?
Exactly, exactly. So basically, map is like converting everything to a list, and then here it flattens all of those lists, right, and give us only like one array, basically, rather than array of arrays.
Gotcha.
Exactly.
Thank
you. That's the second, basically, aspect of it that I will show you in my demo soon. All right. Thanks for pointing that out. Other questions? Everything is good? Okay. No raised hand, no question in the chat box. All right. So those were transformations, right, that are applied on an RDD and they give us new RDD. How about actions, things that return results to the driver program, right? So again, continuing our example, so we have the same RDD. And the first and the most basic action is collect. Collect basically tells the worker nodes to return that RDD to the driver program. As you may imagine it is a very dangerous operation. It is totally safe to do it on this toy example because I only had 3 integers on that list. But if the RDD is like 1 terabyte and you apply collect on it, all of the worker nodes will transfer that terabyte of data to the single machine, which is our driver node, okay? Very dangerous operation. Instead of that, because, okay, how about we want to inspect our RDD to see if the values are correct, to see if the transformations we have developed already are correct. How about that? Sure, you can use take instead. Take returns only a subset of the data to the driver program, and the number that it accepts is the number of lines or number of elements that it has to return. Okay, so it's okay, I have this RDD, it has like 2 billion elements in it, or 2 billion lines, for example, if it's text. Just give me 2 lines. Okay, so that's safer to inspect to make sure, yeah, the format makes sense, everything makes sense. Now we can move on, right? So it's a nice debugging tool. We have an interesting question in the chat box, so I encourage you to read that. So there's basically a question says, if we apply map instead of flat map on nums, and then we apply lambda x to range of x, what happens? As was pointed out, it gives us a list of basically values, right? It's an array of array technically. So, and that's correct, because still we have the one-to-one mapping, right? Because the first RDD has 3 elements, and what is produced is also has 3 elements, right? Because it has 3 lists, so everything is fine. So it works, but it gives you a list of lists in Python, right? Or in Scala, like an array of arrays, right? And then flat maps just flattens those inner lists and gives you only 1 list or 1 array. Make sense? Thank you. That was really good. So we have another question. So if we apply take 2 on an RDD, does it return 2 elements or 2 lines? They are the same, right? So if the data type that you're working with is text, then then each element is a line. But if you're working with numbers here, every element is a number, for example. Make sense? That's why I sometimes switch between elements and lines. So if you're working with text, you can say every element or every line, they are the same. Let me know if I answered your question. So does flat makes a single element? So flat map gives you like 1 array with all of the numbers in it. So I would say to 1. So that one, it gives you that one, not the list of 1. So flat removes the lists, right, and flattens the list. So if I go back to that slide, so it really returns something like this, right? And there's no inside the square brackets. Map gives you this with inner brackets, but flat maps just flattens that and removes those and gives you just a list of numbers. I'll show you an example in my demo. I'll show you an example in a second. That's an important thing. So make sure everybody understands it. I will explain more. The next action is count. Sometimes instead of inspecting the RDD, the content, we want to know how many elements we have in the RDD, right? So the easiest way to do that is to apply count. Count tells you how many elements you have. And for example, on my stupid example of like 3 elements in the RDD, it returns 3. And then we have reduce. And we have another thing called reduce by key. So don't confuse it with that, okay? Reduce by key is a transformation, but reduce is an action, which means that it returns the stuffs to the driver program. It doesn't create a new RDD. What does it do? It basically collapses or aggregates all of the elements you have in an RDD using the given function, and it gives you a single element probably. Okay, so in this example, it says reduce all of the element in nums RDD by this function. So take two elements like x and y and add them up. So what it does, it take 1 and 2, it will be 3, and then again it takes the result of that, which is 3, and adds it with 3, it will be 6. So it adds up all of the numbers and it returns 6 to the driver program. Again, a safe operation, a safe action, right? Because it doesn't return you the whole RDD, but rather the result of reduce, which is the aggregated result, which is fine. We got another question. If f function f that accepts x returns a 2D list, and then we apply something like, okay, we apply that function and using flat map, is it still, I believe it is still two-dimensional because it doesn't mess with the content, right? It just removes the lists that are produced as the result of mapping, right? It doesn't change your data. Because I think if it converts everything to one-dimensional list, that's modifying your data, right? We can try it. We have Spark Shell. We can quickly test all of these things. And finally, these are good questions, by the way. Finally, one of the things that we want to do is when we are done with all of the operations, we don't really want to return anything to the driver program, but rather we want to store the results because the final RDDs still contains a lot of data. So we don't want to return that to the driver program, but we want to store it, right, for further processing or some other reasons. So a very useful action is save as text file, and it takes whatever RDD that you have and stores it to the default file system that you have, or if you explicitly specify what type of file system you want, stores it to that file for you. So we got another question. What kind of operations are we allowed to use in reduce function? Is there any consideration here? So basically, it should have like two elements like x and y, right? And then an operation here that aggregates them, right? Like multiply them, add them, something like that. So it should be an aggregation function, right? That kind of combines. Don't confuse with the other combine the elements somehow. If I think some students who took functional programming, this is probably very familiar for them, right? It's the same thing. All right, enough of the slides. Let's write some programs, okay? Actually, let me. Sorry, I want one more slide here, and then we continue. Well, we work with key value pairs. Okay, very common data structure in data science. And for you guys, you should look at the Scala version, right? And the way you can define key value pairs, simple. So parentheses, A and B, key value, and then how to access the elements. It's very easy. So it will be that variable dot underscore 1 or dot underscore 2. 1 is key, 2 is value. It doesn't start from 0. Okay, ugly. Remember that, okay? 1 is the first element. And a few operations that we can do on key value operations. So again, you can feed it an object from the host program, right? So you can use parallelize to convert these key value pairs into an RDD. And then you can apply some operations one is reduce by key, is a transformation. Don't confuse it with reduce, okay? So reduce by key is a transformation that takes an RDD and gives you another RDD. How? It says, okay, this is exactly like Hadoop reduce by key. So you guys know it, okay? And then this function that we define here is like the operation of the reducer, right? So it says, okay, how should I reduce by key? It says, okay, take basically if you find two identical keys, do this to the values, okay? It's just, okay, add up the values in this case, right? So for example, we have cat1 and cat2, so identical keys, cat, right? So we aggregate, and then how should we aggregate? Well, add up the values. So we end up with cat3 and dog1. There's no other dog, so we cannot reduce it further, right? So that's an operation, very useful, very useful. So if you want to model Hadoop in a Spark, it's basically applying map on an RDD and then apply reduce by key. It's pretty much like Hadoop, right? But we have much more flexibility in a Spark, right? We have group by key, okay? So we can perform the aggregation, but we don't actually reduce, right? So for example, here we have cat 1 and 2, right? So we just perform group by, we don't reduce them. So we keep a list. And then we have sort by key if you want. So it takes the keys and sort the elements for you. So here, because we have a string, it will be alphabetically, right? And it doesn't perform any sort on value. So the fact that this is 1, this is 2, is random, okay? It could be the other way around. So we are just sorting based on keys. So C is smaller than D. So that's why cat is smaller than dog. And now we are ready to program. There you go. Can you see the terminal? Cool. So I logged into DataSci using my personal account. And I can get access to Spark shell. So obviously you have a Spark, the standalone version or the regular way of calling the Spark, which is pretty much like Hadoop. So you write your programs and then you call Spark, pretty much similar, like very similar to the way that we call Hadoop. But Spark provides the shell as well, which is an interactive shell, really nice. We can just try out different things. It's a very nice addition that Hadoop did not have. I will use it for my tutorial. All right, it's loaded. So a few things to mention. So as I told you, a Spark context, which is the entry point, is already created for us, and it's accessible using this variable sc. Okay, and here, and also in the other version of programming, it's a Scala, right? It's the host language, right? So I can just program in a Scala here, like for example, test and array of 1, 2, 3, right? This is a Scala. This is not a Spark, right? And if I do test, it's an array, so it is the driver program. So it's in the memory of the driver program. Make sense? No Spark yet. Now let's use the entry point to Spark and let's create an RDD using that array that we created, okay? So that would be like RDD, or like my RDD, let's call it, stupid name, sc.parallelize, and then here you can just type array 1, 2, 3, or you can reuse that variable that you have. So you can say test. Okay, I'll show two demos. One is in a Spark, sorry, one in a Scala, and the other one is Python for non-CSS students. And I make mistakes, and you can make fun of me. All right. So now I created an RDD. It's a Scala, so I had to have val or var at the in front of the variable name, right? So it said that I created an RDD for you. So as you can see, this is like in a Spark RDD object. The data type is int, right? It understands that we had an integer array to begin with, and it provides a reference. Now, if I type my RDD, it again returns that reference, okay? The shell is like the driver program, right, that we have here. So I don't have the content of that RDD here. Makes sense, right? The content is on the worker nodes, right? So in order to get access to the content of this, so again, it's very different from the original array that I have. That's in the memory of my driver program, so I can access it, but not my RDD. In order to get access to RDD, you can do collect. Dangerous operation, totally safe here, right? Because I only have like 3 elements. So now it goes ahead, asks the worker nodes, hey, pass me the data, right? And now you can see it's identical to the array that I had originally, right? Makes sense, right? So that's the difference. So simple things, but I want to make sure that you completely understand what's going on. Is there any question about this? Are you happy with this? Okay, so we have a question. If you are running this locally, then the worker and driver nodes are on the same machine. I'm on data side, so no. So they're all worker nodes. So I'm running this on an actual cluster. I don't think so. It's not the same machine. If I was running this on Linux servers, then you're right. Then it's the same. Good question. If you collect, then my RDD might not be available later, right? And that's a good observation. So this first time we have an action, that's when we actually create everything, right? So when I did this, it was lying to me. It didn't do anything, right? Until I actually collect. If I was reading a file instead of parallelize, and there was like the file name was wrong, still it would say, oh, everything is fine, life is good. And then when you say, okay, collect it, and they say, oops, the file name is wrong. So it doesn't do anything after that. And then the question is, if you do another collect on it, for example, or do another operation, does it mean that my RDD may not be in the memory of the worker nodes? Yes, it's possible. It's possible. But typically, like here, I haven't done anything, so the memory is empty mostly. So Spark has no reason to get rid of it, right? All right. Let's, no questions here. All right. So let me move on to a more realistic example here. And I need to cheat this part because it contains a file name. I'll copy it from here. Okay. Not this using Control L. All right. So I am creating a new RDD called text, and I'm using sc.text file to read the text file. I am on data side. Okay, so this file is coming from HDFS, and it's I think one of the files that you might have worked with in your assignments. Okay. And then here, and again, even if I change the file name to something wrong, same thing happens. It does not complain. It's crazy, lazy evaluation. So all right, so it created an RDD, and you can also tell that this is lazy evaluation because it returned immediately, right? The file that I'm reading here, if I remember correctly, it was at least a gigabyte. There's no way you could read gigabyte in like a fraction of a second, right? It returned immediately because it's lying. All right, now what we can do is that, not text again, dot collect is stupid. So we do dot take to see what we have in the file. So if take one, this is a text file, so each element is a line. So this is what we got. So it says that the result is an array of strings, right? And here we have only one element because I only took one, right? And this is like the first line in that file. All right. I do take two. We should return 2 lines. It's a little bit hard to tell when it ends. I think it's here, right? And then the second element starts here. So okay, we could read the file. That's fine. So now we have that text RDD that contains the file, and right, this helps us a lot, right? For us, I mean, we have experience with working with variable, with lists, right? It's very intuitive for us, right? And now forget about that. This is a huge file. It's a variable, right? Just write whatever you want. That's really convenient, right? All right. Let's move on. Let's implement word count. Okay, this is our hello world. We have to implement this every time we do something. So so it is text dot. The first thing that I want to do is to split these because I need to extract words, right? These are lines. I need to extract words. I could use the tokenizer, right, that you had for the first assignment, but or at least something similar to that in a Scala. And by the way, in the next assignment, you will redo assignment 1, but in the Scala. So I mean a Spark. So now, all right. So but I don't have that tokenizer, so I'm going to implement my own stupid tokenizer. Okay. So here it says, okay, for every element here, for every line, right, it's text. So for every line, do this. Just split that line with space. Okay, as you can tell, it's not a good tokenizer, right? I should consider so many other things, but like for the sake of simplicity, let's say this is what we want to do. And here, let me actually store it in something that's called as var instead of val, because I want to change or reuse it later, and it will be results, for example. Okay. So I want to take my text and I want to split it. Let's see what we get. Okay. Again, immediately it says, sure, I did that for you. It hasn't done anything yet. So we can do res.take, then show me the first 10 elements, see what you have done. It says now the result is an array of arrays of a string, right? And so what it did, it took every line, right? And it gave me a list for that line or an array for that line. That's how we ended up with an array of array. Again, we have an array for every line. We have a bunch of lines, so we have array of array. That's why we have this. And the data type is a string, obviously. And then it says, for example, if this was the first line, right? So for that first line, we got an array. And then it used my tokenizer, right? So this is my first token, this is the second token, third token, so on and so forth. I split it with the space, right? So that's what we get. Makes sense? And then this array ends here, right? This is the first line, right? And then I got another array for the second line, so on and so forth, right? So when I do take 10, it's supposed to return 10 lines. Here, it truncates it, right? It doesn't show it. The dot, dot, dot at the end says I'm not showing all of it. So it was supposed to show me 10 lines, basically, because each element is an array here. So, but is this what we want? This is not what we want, right? We want one array of all of the words, right? I don't want array of arrays. Makes sense? I want to get rid of the arrays, and that's basically how flat map can help us. So here I use flat map. Okay. Instead of map, it's the same except that it flattens the second arrays, right? So it removes all of these inner arrays like this, and just gives me an array of lists. Sorry, an array of words, right? Hopefully, let's see if it works. Let's take 10. All right. Why do I get less output compared to before? Before, each element was an array, right? So I asked for 10 arrays, but here, because of flattening, now we have the word. So when we say take 10, it gives you 10 words, right? Makes sense? The type of the object changed. Questions? Things are getting interesting. Any questions? Okay, so this is what I want, right? And I wait a little bit to see if there's any question. And I want to go to next step. So I have tokenized basically all of the lines, right? So now, again, the beauty is that don't think of this as a big file. This is just an array, right? It's just an array. You can just work with that array, right? Spark takes care of the complexities. So now that I have, so I go back, so I just keep adding stuff to what I have. So everything is fine up to that point, right? So I split the lines. Now what I need to do is like word count. I want to emit word 1, right? For every word, I want to create a key value pair where the key is that word and the value is 1. Because later on, I want to do reduce by key. Make sense? Same logic, like just same thing that we had, but in a Spark, okay? So I can now have a map, right, for every element. So for this a word like is, I want to create is comma 1, key value pair. So I map, so for every x, like is, give me key value pair, where the key is that that element, and 1 for the value all the time. Okay, makes sense? And the beauty of the interactive shell is that we can take 10 again to see if it's really what we wanted. Now it says we got an array and the objects are pairs of a string and int. Looks good, right? So we converted is to this. This is what we wanted. Now we can perform reduce by key on this. Go back to that line and then dot reduce by key. You should be done here. Now, how? So there are different ways to implement this. So the classical way of doing it is something like this. So it says for every 2 elements of x and y, you do this, x plus y. Okay, so this is the classical way of defining the reduce by key. Don't confuse x we had here with this x. Okay, there are different things, right? So this is talking about the reduce by key operation. So it says, what should we do with 2 values where the keys are identical? What should I do with the values, right? It says value 1 is x, value 2 is y. Okay, add them up. That's the meaning of this. All right. That's one way. Scala has a crazy other way of doing this. The syntax is interesting and confusing. This does the same thing. Underscore plus underscore. It means take the first value, add that to the second value. Okay. Let's see if this gives us what we want. Okay, so again, enter, and it's lying. It didn't do anything. Reduce by key will take time, right? So now if I say, give me 10 of them, let's see what happens there. Say, oh, now we have to actually compute that reduce by key. And it will take time because the file, again, I don't remember, I think it was at least a gigabyte. So it will take time. Let me know if there's any question. And this was like a downsampled version of Wikipedia. I didn't run it on the entire file, I believe. Did I? or this was the downsampled version. I think this is the downsampled version, 0.1 sample. Yeah, that's like 10%, I think, of the data set. So reduce by key triggers a shuffle, right? Because previously with other operations like flat map and map, every worker node could just take the partitions that it had and apply that transformation on it independently, right? And create a new RDD, and it will host the corresponding partitions, right? But in reduce by key, worker nodes need to talk to one another, right? Because it requires a shuffle. And here you can see that when I run it, it says it's a shuffled RDD, right? So you should expect that it takes time when you want to compute it. It's finally done. So now I have a word, and hopefully this should be the count of how many. So this word appeared 4 times, right? So we are done. So I want to do a few more things, and then we wrap up this lecture. So I want to cache this because it took some time to calculate. So all right, and it was better to even cache it before take, right? But it is probably in the RAM still, so it's fine. Now, the last thing I want to do is that I want to come up with the 10 most frequently used words in this Wikipedia file, right? So this just gave me top 10, but that's not, sorry, this is not top 10, just the first 10 elements of the RDD, right? That's not good for me. So what should we do? So so we're almost there, right? So we have that results RDD. All we need to do is to sort by value, right? The value is the count, right? How many times it appeared. So if we sort by value, we are done. The only problem is that we don't have sort by value, we have sort by key. So how can we actually implement it? So I'm going to show you a trick, okay? It's used sometimes to solve some problem. As a simple trick. So I call this one sorted results. And what I do, I take this, right? And then the trick I want to use is that assuming that we only have sort by key, how can we implement sort by value? So I want to swap key and values, okay, so that I change the position of key and values. I perform sort by key, and then I perform another swap to bring it back to the correct location. That's the high level idea. Let's quickly implement this. How can we do that? So we have those things, okay, and results. You can look at this when we program so that you know what we're working with. So it says I want to apply a map, so I want to swap the locations of key value. So it will be for every x, right? X is remember, we have data type. So x here is a pair, right? It's a pair of a string and int, right? So, or a key value pair. So x, and then I need to get access to the element. So I need to create a new key value pair, agree? Now, but I need to swap. What should I do? So here, if you remember, we said in order to get access to the elements, we have this dot underscore syntax, right? So I want the second one first. So it will be 2, and then the second one will be x dot underscore 1. Makes sense? This will just change the location. And if, again, the nice thing is that we can, what did I do wrong?
Missing dot, like it should be
All
x
right.
dot
Yes.
underscore 1.
Thank you. All right. And we can do the answer is not take, just to make sure everything is fine, right? That's the beauty of the interactive show. Okay, fine, it's fine. So for something like this, we could create the opposite. Now that the number is the key, now we can sort by key, right? So that's cool. So we go back and then we add sort by key. And you may ask, how do you come up with the transformations? Stack Overflow. Just search for, or the API. Okay, I'm the instructor. I should not say Stack Overflow. The API. Search for how to do this in a Spark, and it gives you the correct transformation. So we have sort by key, and then the only, let me look at my cheat sheet. I think we need to add false to it because it will be in the ascending order. We want it to have the descending order, okay, so that the large values appear first. So I think you can just pass false. False means that it will be the descending order. And then I should do the same thing again, right? Because I want to bring them to the correct location. So I do another dot map. And then for every element X, I want a new key value pair, right? 1 or 2? Tell me here. For the first one, 1 or 2?
2.
2?
Yeah.
Yes, because it's on the new RDD, right? It's on the new RDD. So I want this thing to be the first one, and this is the second one, right? So it's basically the exact same map. So it's identical map, right? So the map changes, so we want to change again the location. So it's the identical syntax. And this time I don't forget dot. All right. We are good. If we do take 10, this should be the top 10 most frequently used now. Is that right? I think so. You may say you don't have any action. Why is it doing stuffs? Well, there is the lazy evaluation is triggered partially for some other reasons as well. And here, because I had sort by key, it means that I'm moving values, right? Which means that you may move an element from one partition to another partition, right? So sort triggers repartitioning, right? Your data may move. That's why it took some time to finish it. It hasn't done everything yet, but it did the repartitioning part already for us. Now, if I do 10, that take 10, this will take time too, because it hasn't done it fully. It just did part of the calculation basically for us already, but the actual one will happen here. So if this is correct, this should return the top 10 most frequently words in that Wikipedia dataset. But because of my stupid tokenizer, most of them are wrong, probably. All right, success, I think. The most common word is comma. Okay, that's my tokenizer. Okay, and then dot. Again, my stupid tokenizer, sorry. And then off and in. Makes sense, right? So, so success, we could write that program. Let's answer a few questions and then we wrap up this lecture. I will continue this tutorial. I will talk about more complex concepts next time. Okay, yeah, the other last thing I want to mention is what somebody already did search and found that actually you lied to us. There is another transformation that we could use. Yes, I just did this for the purpose of demonstrating this swapping operation, things like that. I lied. If you search, there is sort by operation. Okay, sort by takes an element, takes a parameter, and that parameter is like what column or what index do you want to sort based on. So it's not just sort by key, but you can basically sort based on any column or any index that you want. So you can apply sort by 2, which is the second element, on result RDD, and that should give you the same results. Good job. Someone asked, what is LRB? That's a token that appears in that text file. I don't exactly sure what that was. I missed one of the questions, so let me go back. All right. Is there no such thing as sort transform so you can do result.sort? I think it's the same thing, I believe, that we talked about. So it's yes. So instead of that, I could just do, I believe, sort by, and if I'm not mistaken, the syntax is something like this. Let me check my cheat sheet. I think it was the same. Sorry, I missed something. It's underscore dot this. You can look up the API for these things. So sort by, I could do something like this as well, instead of this thing that we implemented ourselves. So that's a good thing that we saw, right? Whenever you want to do something, please look it up, right? Because the Spark API is very rich. It's not like Hadoop that has like 4 functions, right? It has so many transformations and actions, and you can always just search to see what's the best way to do it, right? Don't redo stuff yourselves. In many cases, it will be slower probably. Cool. I hope that you enjoyed this tutorial and you learned. We continue. We will look at more fun stuff next time. So look at the actual partitions, what happens, how do we actually read all of these things from HDFS, how many partitions we have, how this is different from running it in Linux servers instead of DataSci. The Linux server is a bad name that we gave, right? This one is also a Linux server. Okay, anyways. We will continue this topic next time and we will wrap it up. So I have another lecture for non-CSS students in about 5 minutes. So let's stop the recording. I will stay for a few more minutes.